Hello everyone, and welcome to my Onshape CAD tutorial series. I should start this video by giving a sort of warning that this is not a beginner Onshape tutorial. I will be working off of the assumption that you already know about basic sketch planes, how to extrude, how to derive, how to use most of these tools up here. I'm going to be focusing mostly on combat robotics and the way that I CAD for combat robotics. I understand that the way I CAD might be different for other people, and I also understand that the way I CAD may be different from the way you CAD. My goal here is just to show you the tools I use and the methods I use whenever CADing my combat robots. So today in lesson one, I'm going to be covering the variable table. Now, the variable table is something very important in all parametric CAD software, but at least in my experience in Onshape, it is very important for keeping your documents organized and easy to update. Now, the way that variable tables work is that they store a table of various variables. So the way you create a variable, you have two ways of creating a variable. You can either create it in the sketch, um, like so. You can either create it in a sketch by using this sort of hashtag symbol and then typing the name, so length and 15. And you can see that this side is now defined by this length 15, and it populates the variable table. You can also create a variable that is not defined in the sketch by adding it to the variable table, say width. And then you can reference that same value in the sketch. And let's define another variable such as height. Say this is 45. And now you have an extrusion defined by these various variables. And you can also update these variables to change the object that you extrude. Now, these variables are also history-based, as you can see on the timeline, but you can also adjust it. For example, I can set my width equal to something like 30, and then set my height equal to width, and it will update, but it is not possible for me to set my length equal to height, because height is not defined. However, if I was to move, let's say width, actually, let's do it this way. If we were to move length to the bottom of the timeline, suddenly height is now definable because it is higher up inside of the timeline. And now, whenever we update width, the change propagates throughout the timeline. Now that we've covered the basic use of the variable table, I figured I'd go ahead and CAD a very bare bones sort of Alex Drive setup, just so you can see how I usually use the variable table in my everyday CAD. Now, Alex Drive is this semi-complicated system where you take the output of a regular drone motor and you put it into two stages of reduction to get a drivable speed and usable torque. Now the style of drive now the style of drive was popularized by the late Alexander Richmond, who was very inspirational. And he probably CAD'd these quite differently from how I do it, but the way I do it is much simpler and easier for me to grasp. So the first thing I do with any CAD is to define my sketch plane. Now, when defining my sketch plane, the first thing I usually start with is a master sketch. This sketch is made completely using construction lines, and it is used to sort of set up all the variables, and it also contains all the references I use later on in my CAD. So the first thing I'm going to do is sort of consider the reduction I want. Usually you should be aiming for something like 5.5 to 1, something like that to get a usable traction. To get a usable sort of reduction in your Alex drive. So the first thing I'm going to do is to define these two initial gears. So I will be using this first. I'll be using the spur gear and this sort of secondary spur gear. I will be setting the secondary spur gear on the origin and setting the output spur as the secondary gear. I do this because I consider this to be the centralizing factor, as it is also the center point for all of the belts. Now, the first thing I'm going to do is set these two circles tangent together. Then I will define two variables. My first variable will be primary spur diameter, and the second one will be secondary spur diameter. I will also be naming my gear module gear mod primary spur teeth and secondary spur teeth. So for gear mod, I will be creating a ant weight reduction. So usually something like 0.8 is quite good for, or quite usable for ant weights. Usually if you're going to be 3D printing gears, you need to keep the gear mod under 0.8 because any wider and most nozzles won't be able to print them with enough accuracy to be usable. If you're creating something like beetles, I'd actually recommend a higher gear mod, something like 1 or 1.2, just so that it's easier for the machines to manufacture. In this case, I'm planning on 3D printing these gears out of nylon or a similar material, so I will be sticking to a lower gear mod of 0.8. For my primary spur teeth, I will be using 12 and making sure to set the value or the variable type to a number. So 12, and then secondary will be 24 to get our 2 to 1. And now in order to get your tooth diameter, you simply multiply the gear mod by the primary teeth, gear mod by the secondary teeth. And now we want to dimension secondary and primary. And then what I'm going to do is create a reference line, secondary line, and set a stir angle. Set this as an angle, and we'll just stick with 45 degrees. Alex and his CAD used a higher degree. This is just for clearance of the motor. Once again, the advantage to using a variable studio is that you can update this value whenever you want through the variable table, and it will update throughout the entire CAD. Sorry, spur angle. As you can see, if I decide that I want a higher spur angle, I type it in and it will update. Let's keep it at 60 for now. And you can see my sketch is entirely in black. That shows that so far it is fully constrained. Next up, I'm going to create two circles and some lines in between. This will be used for determining the belt distance. Constrain these. Now these two lines will be used to constrain the belt distance between two wheels. If your two wheels are the same size, you can get away with using the same reduction. If they are not the same size, then you will have to use a variable reduction with different sized gears. I want to keep this simple. So in this case, we can actually just set, if I'm going to, sorry. In this case, I want to keep things simple. So I will keep these two wheels as the same size, which means that these two values will also necessarily be the same size. So what I can do is set these two diameters the same, and then set these two line lengths also as the same. And we can also draw a tangent line to both wheels and ensure that it is horizontal. Next, we will define wheel diameter. Let's say something arbitrary like 1.5 inches. And then we will define our wheel clearance. Or I guess it should be spur. Primary spur height. And let's name that something like 20 millimeters. This will ensure that there's enough clearance between the ground and the gear. And finally, we are left with our belt length. Now, depending on the sort of reduction you use, this length will be different. So, in order to capture that, we should consider our belt. So, as you can see here, our two drive sides are belted to whatever tooth value are on these pulleys. So, primary teeth and secondary are, let's say, pulley teeth. Set these values both to number. And let's go for another 2-to-1 reduction. So let's do something like 11 to 22. Now I would draw these again, or I would use something on the sketch to show these, but there's really no reason to. Now, what I do write for my own information for when I'm buying belts is to write the belt teeth as well. Although this value is never referenced in the document itself, it's simply used for me to record what belt I should use, and then I record my pulley distance. Now, what this pulley distance does is it defines this length. And this pulley distance is used to reference the length of this line over here. It tells me how far I want to define the wheels from the center. So usually I use a belt calculator tool, such as this one by B&B Manufacturing. I set it to metric, HTD 3 millimeters, and I check however many tooth, so 22 to 11. A large pulley is 22, small pulley is 11. The belt width doesn't really matter. And then we want to set an ideal length. So pulley distance and an ideal length. Let's start with something like 35, maybe. Seems like a usable amount. Maybe I want a bit more clearance. So let's start with an ideal of 40 millimeters. Set. This teeth and mesh warning is really not that big of a deal, but we can see here that the ideal center distance is 40.9. Now with Alex Drive, you actually want to undershoot this value a little. This is purely vibes based. In the description, I usually write true value. as 40.9, and then I usually round down or subtract a few millimeters just to give the belt some more slack to sort of minimize the resistance that the drive system encounters. You don't have to do this if you're using metal parts. If you're using an Alex drive system, that's something you might want to take into account. Now we have our basic drive system. Now I will name this sketch as Alex Drive Master Sketch. And this is also the sketch that we will sort of base everything off of. Let's go ahead and add a few more values to our variable studio, and I will get back to you in a moment. All right, we are back. So the first thing to note with AlexCAD is that the wheels have to be a bit offset off of each other. You can see that the reason for this is because it is impossible for the belts to be perfectly aligned. Now, there's two ways to go about this, and I will show you the simpler way. The more complex way is what you can see with Alex, where he chooses to split the wheel. You can either split the back or the front wheel, and in his case, he uses cleats in order to split the wheel, but you can also just have two pieces of molded urethane instead of one piece. My method will be simply to offset the wheels. What you do is you want your inner wheel to be closer to your center of rotation, and your back wheel to be closer to the center of rotation, and your front wheel to be closer or further away from the center of rotation, and you simply have an offset between the two wheels. So the first thing I'm going to start with is the sort of initial spur gear reduction. I'm going to use a feature script called spur gear, and I will go ahead and select the mating here and set the depth at ear depth. Something like 5 millimeters is honestly fine. Secondary spur teeth, then gear mod. Then I will create a secondary spur here, or a primary spur here. Ear depth, primary pulley teeth, and gear mod. Why is it not lining up? Primary, secondary. I believe I typed one of these incorrectly. Secondary. I think I defined. Oh, I didn't. That is my mistake. I didn't actually multiply it by gear mod on the master sketch, but that is something easy to fix. There we go. And we can see that the gears mesh together. Now, you can also notice that they don't mesh perfectly together in our part studio. That is okay. That is something that can be fixed by reanimating in the assembly studio. It's not super concerning for what we are doing right now. You might also want to take this and specify our not a way to do it on gears. Is there not a way to specify our bore, center bore? And Set that as our axle diameter. Great. Now we create our sketch here. And this is going to be our initial belted reduction. Actually, I don't think you want to create sketch. You want to, I will be using another custom feature, and I will be using the timing belt feature script, setting this, and then making sure it's on S3M, and setting it as our primary pulley teeth. Perfect. And then I will be extruding this out, belt width times 2 to give the clearance for both belts, and then I will add 1 millimeter to give them some room to slide around, and then I will add 3 millimeters for the sort of retaining feature. Then I will create another sketch, create a circle. This is kind of just like an arbitrary dimension. It doesn't really matter. You just want it to be enough to constrain the belt. Let's do something like 15 or 14. That's fine. And then extrude this in by the same amount. And as I'm doing this, I want to talk about the pros and cons of parametric CADing. Especially when people first start out with parametric CAD, you might feel a pressure to do everything parametrically. It is an option, but in my experience, it's not the most efficient way to CAD. The most efficient way to CAD is to parametrically define a master sketch and then sort of CAD semi-normally from there. Now that I have these two values, I want to go ahead and define my wheels. So what I'm going to, is to define the location of these secondary wheel pulleys. So the first one's very easy. We simply create an offset plane and set the offset to 0. And we will label this as front wheel plane. And then we will go ahead and offset the plane here, belt width, and we will label this plane as back wheel plane. So now we have 2 planes that mark where the belt path is expected. Let's go ahead and start with the front wheel pulley. Sorry, let's go ahead and start with the front wheel pulley. I always try to create a sketch, but the spur gear feature script does not need, actually it does need a sketch because we need to define it on the sketch plane. So we simply click this circle on the master sketch and then press U to derive the sketch onto our current sketch plane. And we will go ahead and do the same. We will go ahead and do the same on the back wheel plane, clicking the back wheel and then deriving it onto that sketch plane. At this point, we can go ahead and hide our master sketch and go ahead and hide our planes. And you can see we have 2 secondary sketches that are derived from the master sketch, but they are offset on the correct plane. Now we can go ahead and create our spur gear using our feature script. I wonder if I can select multiple. That'd be really convenient. I cannot. Okay. No, sorry, I don't want it to be a gear. Timing belts. Go ahead, click here. No, you cannot. All right. Drive pulley and timing belt. Drive pulley. And now that we have these pulleys done, we can go ahead and extrude both of these as belts width plus our 1 millimeter to give them some room to slide, plus our 3 millimeters for the cap. Now there are two ways to do this actually. I'm actually going to delete the secondary one. Um, I just thought of a easier way of because you can because these are actually the same gears. I don't see a reason to create the same gear twice and create the same sketch 2 times on 2 different faces. That seems like a lot of extra work that I would rather not do. So instead, I will only create one gear in the cap and then extrude this 3 millimeters. Now, in a case where you have two differently sized wheels, you will have to just do this 2 times. There's not really a way to make this any less painful. Okay. Now we are going to create a sketch here and draw our wheel diameter. And we will extrude this. Now, not wheel diameter, wheel width. Now, obviously, this is a very simplistic model of Alex Drive. In a lot of cases, this part would not be the entire wheel. Obviously, you would have to create your own retention hub for either foam wheels or urethanes. I will not be going into that. This is supposed to be a simplistic tutorial. Now we will use the transform tool and translate by mate connectors. So select this mate connector, click copy part. And nope, I clicked the wrong mate connectors. You don't, because you want to derive it off of this inner circle to get the correct offset. Perfect. And now these wheels are staggered. This becomes our front wheel, this becomes our front wheel, this becomes our back wheel. And we have our Alex Drive almost done. Let me just do this. And now we have a basic Alex Drive system that is fully updatable depending on our variable studio. For example, let's say, oh, I want a greater reduction on my secondary spur tooth. We can bump this up to 36. And the entire CAD should update. But sometimes these you can never remember which one you're supposed to use to fully define it. You're not supposed to put in the module. There we go. And now it'll match. Let's go ahead and fully fill out this one. For some reason, I can never remember to also place in the pitch circle diameter, so that is on me. Primary pulley teeth times gear mod. So now if you're in the case where for some reason you want to increase the amount of teeth in your primary spur teeth, maybe you find that you want like a lower reduction, you can type in a different one and it will update. Let's say you want bigger wheels, you can simply find uh, your wheel diameter and update that, and everything will update. Oh, oh, I didn't specify. Set it to 2 millimeters instead of 2 inches. There we go. Or if you want something like you want your pulley distance, let's say you recalculate and you want it to be further away now that your wheels are bigger, you set it to something like 55, and your wheels will suddenly be more spaced. Hopefully this video shows you how powerful and useful of a tool the variable table is. It helps a lot with, you know, saving time and effort whenever you're creating your parametric CADs. And also you can hopefully see that it spares a lot of time during the actual CAD process and when debugging, just because it streamlines your CAD process. Uh, I have some more beginner topics that I would like to cover, such as design ideas behind basic weapon design, fork design, and robot design. If you have some specific topics that you would like me to cover, I'd be very happy to cover them in future videos. So please leave a comment and I will see what I can do.